So what is wave motion? Wave motion is transfer of disturbance through a medium or empty space. And actually there is only one, which is also known as vacuum. There is only one type of wave that can transfer through empty space, and that is light. Okay. So a transfer of disturbance, which is also a transfer of energy. All right. So the wave motion in one dimension would the general one would look like this. Okay. And this the highest point, it's called a crest. The lowest point, it's called a trough. Okay. These points here, and there are many, are in equilibrium. Okay. And now it's a time to actually introduce there are types of waves such as transversal, longitudinal, and whatnot, which you may have talked about them previously. We're going to focus on transversal waves, which is light is one of those types of waves. All right. So let's introduce the wave characteristics as we may have done them before. So again, I'm going to draw two graphs here. One is going to be y versus x, so it's like a snapshot in space of a wave. And the other one is going to be y versus t, so it's over time. Okay, so they will look the same. It doesn't matter how we start them. All right. And now let's talk about the characteristics. So of course, the distance from the equilibrium, it's called amplitude. Okay, the distance between 2 points in the wave motion that are behaving exactly the same, it's called wavelength. Okay, the time it takes one complete cycle to complete, it's called period, right? This is measured in seconds. This is measured in meters. Now, the amplitude for mechanical waves is measured in meters, but for a light wave, it's an electric and magnetic field. All right. And then we have the frequency as well. So let's start listing them. So wavelength, we use the Greek letter lambda. It's measured in meters and is distance between 2 points behaving the same. All right. And then we have A for amplitude. And again, the units will vary depending on what kind of wave we're dealing with. So it could be measured in Teslas, it could be measured in newtons per coulombs for light, and pretty much is how much does the quantity that is acting on a wave type of motion is far from equilibrium or zero. All right, so for magnetic field and electric field, for the light wave, at a certain moment they are at the zero level, 0 Teslas, 0 newtons per coulombs. The next one is period. Okay, period is measured in seconds, is time for one cycle. Okay, then we have frequency, which is measured in 1/second or hertz, and that is the number of cycles per second. All right. Then we have energy of waves, the energy they carry. We have the intensity. We have many more variables, but these are the basic one we're going to deal with. And there is one more when we compare two waves, and that is known as phase shift. Okay, could be measured in meters. All right, could be measured in degrees, but pretty much this is the distance between two sources, and usually we're going to express that in terms of wavelength. Okay, so again, the phase shift can be represented in degrees, as you've done in math, and other in radians. But here we're gonna to give you an idea of what it means is if I have 2 points here, two sources, so source of a wave here and another one down here, and they're both emitting some waves, okay, and they're going like this, and this is a point P in space, okay. So this is the actual path that wave number 1 has to go through. This is the path that wave number 2 has to go through, and the distance between the paths of these two waves, if they're not equal, that is the phase shift, or we call it also delta R or delta T. Okay, so that is those are the main characteristics of a wave that we will use throughout this section of wave nature of light. Okay, the wave equation, it's only one. It relates the wave speed of a wave. Okay, so it's very simple. The speed of a wave in general is distance over time. But bear in mind that a wave moving through a uniform medium or through space, it's a uniform motion, okay? So it does not accelerate, slow down, or speed up. It has constant speed. So we can use very simple kinematics, okay, distance over time. But we know that we have a very specific distance in waves, such as wavelength, and we have a very specific time for a cycle to be completed, such as period. So it's lambda over t, okay? But since we know, and I'm writing it down here, that frequency, which is, remember, the number of cycles per unit of time, is equal to 1/period. Remember that period is how long does it take for a number of cycles to complete it, right? So it's a time for one cycle, right? So since frequency is the reciprocal of period, then the wave equation in standard form is V equal to lambda times F, okay? Now the speed for light, the speed of wave of light wave is c, okay, which is 3 times 10 to the power of 8 meters per second. Bear in mind that that is only in vacuum, or roughly in air. In other medias, the light will slow down. So for light, the equation becomes c equal to lambda times f, okay? Should light be a wave, which we will show it, that yes, indeed, light is a wave, okay? So that's the equation, the main equation for any waves, mechanical or light or sound, okay? So now we're going to talk about phenomena associated to waves. So those are there are many. There is reflection, there is transmission, there is diffraction. We won't talk about it here. There is interference, okay? And then once we deal with them in one dimension, we're going to see how they look like in two dimensions, okay? So let's start with reflection. So pretty much what happened now is that the question is, what happened to a wave when there is a change in medium? All right, and a bunch of things can happen. A change in medium means that density has changed, okay, and or elasticity. All right, so the type of medium. So you're going, for example, from air to water, from air to glass, from glass to air, or anytime that there's a change in the type of medium, there is some phenomena that will occur, and one of them is reflection. All right, so we have two types. Is when a wave goes from a medium that is low density to another medium that is high density, and as you recall it, we call that a fixed end. Okay, and what happened is that the wave will actually reverse. Okay, will be inverted. So this is the reflected wave, and this will be the transmitted wave. All right. The way how I would write this is that, sorry, this is the incoming wave. Okay, so I is for incoming in my notation, and R is for reflected. Okay, so incoming is out of phase with transmitted, reflected. All right, so when we have a fixed end, so what does fixed end means? Fixed end means that you're going from low density to high density. In terms of light, that is related to index of refraction. Okay, so this out of phase, what does it mean? It means that the two pulses are completely opposite. They are behaving the opposite. When one goes up, the other one goes down. All right, so very briefly, let's talk a little bit about the phase here before we continue. Remember, we introduced phase earlier. So let's say I have two waves. One is like this, okay? So here is source number one, okay? And then there's another one that happens to be exactly the same, but in what happened to that one, it has started from here. This is source number two. So as you can see, in the space where they are traveling together, they look exactly the same. All right. When you see two waves like that, that they match each other, you cannot even tell them apart. It means that they are in phase with each other. All right. So remember what I said, that we're going to talk about phase shift in terms of distance between the two sources. All right, and you can see here that the distance between the two sources is actually a wavelength. All right, could it be zero? Yes, it could be. S1 and S2 are exactly the same place. Could it be 2 lambda? Of course it could be. Okay, so in general, two waves are said to be in phase when the difference in path is some multiples of lambda, where m is a whole positive number. All right, is 0, 1, 2, and 3. What we're doing here, we're talking about, in order to make sense of this equation, coherent sources. What does it mean, coherent? It means they have the same frequency, all right? They have the same amplitude, and pretty much they have the same behavior. So which means when one is up, the other one is up. When one is down, the other one is down, as you can see here, right? Both of them, imagine of having two ropes, two people, S1 and S2. They are both moving the ropes at the same time, starting from up and then down, okay? So this is in phase. And of course, we have the out of phase scenario. And these are the two extremes that we're really going to deal with in this course. There is, of course, plenty in between. But out of phase is when you have something like this. So again, let's have one wave that is as such, and this is the source of that wave. And we have another one, let's use the same color, but now the other one is completely the opposite. All right, so which means, and remember the S1 and S2 have to be coherent sources, so which means they both have started in the same way and then both are having the same frequency, the same amplitude. As you can see, the two waves are behaving completely the opposite, right? When one is up, the other one is down, okay? And again, when does that occur? When the two sources are at distance, as you can see, is half of wavelength, all right? So out of phase, which means the two waves are behaving exactly the opposite. The distance between the two sources, it looks like it's half of lambda. And of course, what could be the next one? Could be 1.5 lambda, 2.5 lambda, all right, and so on and so forth. So which means it looks like the difference in paths between the two sources, between the two waves, should be some multiples of half lambda, all right? So how do I write that? Remember, 1 and 1/2 is 3 over 2, 2 and 1/2 is 5 over 2, and so on and so forth. So it looks like some odd multiples of half, right? So it's 2m plus 1 half lambda, all right? Where m, it's still a whole number. So it's 0, 1, 2, and so on and so forth. So this is the condition for two sources to be completely out of phase. And of course, as I said previously, we have in between. So, but in general, we have, for example, something like this. Okay, and then we could have a source that is just slightly off the phase of the other one. Okay, so again, this distance here is neither of them. So this is in between out of phase and in phase. So it could be like a quarter of a wavelength, for example. All right. So now let's go back to our reflection. So remember, we were here. That's why, since we use that term, I want to make sure that we cover that. So remember, when you're going from low density to high density, or a fixed end, the incoming is out of phase with the reflected. All right, let's remember that for later on. And the other case is when you have a free end. Okay, so when you have, so I'm writing here free end or open end as it's known. Free end means you're going from high density to low density. And in this case, you have a wave that is going through. Remember that you used to do this with a rod and a ring, which means this is free to move. All right, and what happened is when the pulse gets to that end, where there is that change in medium, the actual transmitted or reflected pulse will be, sorry, the other way, will be also on the same side as the incoming. Okay, so what can we say in terms of using the same terminology, in or out of phase? The transmitted, again, the incoming, we'll talk about transmission later. The incoming is in phase because they're going to match each other with reflected. All right, reflected wave. They're going to be exactly the same. Okay, so that's the reflection in of waves. There are two types again: free end and fixed end, or from low to high density and from high density to low density. So in terms of light, the first case here, when you go from fixed end, from low density to high density, to give an example in terms of light going from air to glass, or to water, or to oil. Okay, in here, going from high density to low density is the reverse, going from water, for example, to air. All right. So now we can talk about the next phenomenon associated to waves. What happens when waves travel the same place at the same time? Okay, which is known as interference. Okay, so when two waves travel through same space and same time, they will interfere. Okay, and we had they will interfere, and we had two types of interferences. If you remember, we had constructive, when the two waves were both in phase with each other. Right, so this is incoming 1, this is incoming 2, and what will happen, so remember, these are in phase, right, or both upright. So what happens in the middle, we will have that super crest, right? So we're going to have I1 plus I2, okay, during interference. And what would happen after is that the two waves will travel as they never met with each other before. So I2 will be on the left and I1 on the right. Of course, we could have the other case. So this is in phase, constructive. The other type of interference is destructive interference. Okay, when the two waves or pulses are out of phase. All right, so in this case, it's one is up, the other one is down, so I1, I2, and they are traveling against each other. When they meet each other, pretty much we have the two overlapping. Remember, it's like pulling against each other. If you're talking about electric field or magnetic field, one electric field is up, the other electric field is down, the net electric field is 0. All right, so it's like it's not there. So if I were to do it like this, this is E1, this is E2, and the net electric field is actually 0. Okay, so they cancel each other out. And then, of course, they would keep, sorry, it's the other way around, they would keep traveling like they never saw each other. Okay, so this is I2, this is I1. Okay, so they pass through each other. Okay, that's destructive interference. Now let's think here a little bit. What do we mean? So what will this, if we have two sources of light? Okay, so for two sources of light, I1 and I2, let's say two red lasers. Two red lights. Okay, remember they have to be coherent. So if we were to observe an interference between two sources of light, what do you think constructive interference would look like? And what do you think destructive interference would look like? All right, so very simple. Constructive, remember, for sound, constructive interference was higher, louder sound, right? Destructive was quiet. For light, constructive will mean brighter light, right, with high intensity. Destructive, it means dark. All right, so that's what we are going to be looking for when we talk about interference patterns for light wave, right? Because to convince ourselves that light is a wave, we have to show that they interfere. A little bit of history here. There was this, let's call it, war between Newton and Huygens at the time. That one was the pro-wave nature of light, and Newton was, of course, pro-particle nature of light. And anytime there was discussion about reflection or transmission or diffraction, Newton was able to explain all those phenomena using particle theory, okay, conservation of momentum, acceleration, and all that stuff, okay? But conservation of momentum was his main point. However, interference is something that cannot be explained using particle theory, okay? So if someone were to conduct an experiment to show that light would interfere, would show interference patterns, so which means would show these dark and bright spots, then you certainly have shown that light is a wave indeed. And that's what Young did with his famous double slit experiment. And that's where all this lecture will lead into, all right? So let's put some more information here, prior information, before we go into those experiments. The index of refraction, as you remember, index of refraction is the ratio of the speed of light, vacuum, and through a medium, right? So C is in vacuum, and V is in at a given medium where light always will slow down. So always V is less than C. Okay, so we expect N to be greater than 1 in general. So what happened when light, now that we're gonna, so here is, we know that light is a wave. So here is, let's say, air, and here is glass, okay? So there is a certain frequency, okay? So this light has a certain frequency and a certain wavelength here in vacuum, okay? And then it goes through the medium. So we know it slows down. So what happened is the crest, they get closer together, okay? So what happened is that slowing down, this is what it means, okay? That this disturbance will travel slower. So there's going to be a frequency here through glass, let's call it medium, and lambda through this medium, okay? What happened is that the only thing that will change is the wavelength, all right? This is a lambda through vacuum, that's a lambda through medium. Remember that the speed of light in vacuum is C, which is F times lambda on vacuum. And of course, it slows down here. And the frequency does not change. It's still the same number of cycles because it does not depend on how fast it's traveling. However, the wavelength will get shortened, okay? And since we know that if I have these two equations here, and we know that N, which is index of refraction, is C over V, which is F times lambda, the wavelength of that particular light in vacuum, over the same frequency times the wavelength of that particular light in a given medium. The frequency is the same, so therefore we can find out that the lambda at a given medium is actually the lambda in a vacuum over the index of refraction. So let's remember that the wavelength when the light travels through a medium will actually decrease, all right? So as n, the index of refraction, increases, the wavelength on that particular medium will actually, on a given medium, will decrease. So the wavelength of red light, for example, in vacuum is greater than the wavelength of the same red light in water, okay? So that's what we need to know about the index of refraction. And now we can talk, for the last thing that we're going to talk is transmission, of course, since we're talking about medium. Very simple. Transmitted waves, no matter what, so I'm going to leave it short here. Transmitted wave through a medium is always, okay, so very simple, it's always in phase with incoming wave. Okay, so it won't change like it was in the reflection. It won't change side. It won't be out of phase or whatnot. So if I have a wave traveling through air, when it hits this boundary, and let's say it's going to glass, then the transmitted wave will be still the same, and then the reflected one will be inverted. All right, so we have reflected, we have incoming, and then we have transmitted. Okay, so that's all we ought to remember for the wave. So remember, we talked about the general information we need to remember before we go into the new content: the characteristics, the definition of waves, the wave equation, reflection, interference, the conditions for constructive and destructive interference, the phase shift, okay, and the index of refraction, how the wavelength depends on the index of refraction. The next thing is now to apply all this information to a wave in 2D. Okay, what happens if the wave is traveling in a plane?